Hello students, welcome back to yet another session on chemical kinetics. But before that, if you haven't subscribed to my channel yet, please do so. And don't forget to hit the bell button so that you're updated about my notifications. So on that note, let us begin with my today's session. Our session today is on the integrated rate law. Now in mathematics, you must have learned about integration. So integration is nothing but the summation or sum total of a set of values lying within a limit from the initial to the final value. Okay, so here this integrated rate law in chemical kinetics gives us the relation between the rate of a reaction and the reactant's concentrations at different points of time. Whereas in the earlier session, we have defined what is known as the differential rate law, where we express the rate in terms of dA by dt or in terms of dV by dt and so on. So those differential rate laws or the terms dA by dt indicates the relation between the rate and the concentration of the reactant at any one instant of time. So today we'll be studying the integrated rate law first for a first order reaction. And in my upcoming session, we will take up the integrated rate law for a zero order reaction as well. So what is the integrated rate law for a first order reaction? So we need to derive an expression for this first order reaction. So let us understand the procedure for the derivation of the integrated rate law for a first order reaction. So in this case, we need to consider a general reaction as a first order reaction. So because the reaction is in first order, we consider a reaction where there is only one reactant. Let us assume the reactant is A. So we have to take only one reactant so that the order of the reaction remains as 1. Okay. If I take two reactants, then minimum the order will be 2. Or it may not depend upon the second reactant anyway. So we better start with just a single reactant. So let us assume that A is getting converted into products. Now, how do we define the rate of this reaction? According to the basic definition of average rate of a reaction, we can say the rate of the reaction is nothing but minus dA by dt, right? We can also define the rate of reaction in terms of the rate law. The rate law says the rate of the reaction is equal to K, that is the rate constant, into concentration of reactant raised to 1, since this is a first order reaction, right? So now both these expressions denote the rate of the same reaction, and hence we can equate the right hand sides of these expressions. So we get minus dA by dt is equal to K into A raised to 1, or that is simply K into A, concentration of reactant A. So this expression, that is minus dA by dt is equal to K into A, this is called as the differential rate law. Please keep this in mind. We'll be using this in the later part of the session. Now, we need to integrate this differential rate law. So for that, we bring the similar variables together. So I take dA upon A on the left hand side and I shift the dt to the right hand side. So I have dA upon A equals minus K into dt. Now let us integrate this particular expression. So for integrating, we need to apply the limits. So the limits will be from the initial value. So initially the time is 0. So when t is equal to 0, the initial concentration of the reactant A, let us denote it by A0. And at time t, that is the final time, some time t, the concentration of the reactant A will be denoted as AT. Alright, so these will be our limits. Time will be from 0 to t, and the concentration will vary from the initial concentration A0 to the final concentration AT. So let us integrate the differential equation. That is dA upon A is equal to minus K dt. So when we apply the integral from the limits A0 to AT for dA upon A, this is equal to, K is a constant here, so we keep K out of the integration. So I have minus K integral dt from the limits 0 to t. Now what is integral dA by A? You must have learnt in mathematics that integral 1 by x dx is log x. Similarly, this is integral of 1 upon A into dA. So this is log A. Whereas on the right hand side, you have integral dt, and that is same as your integral dx. Integral dx is x. So here I have integral dt is equal to t. We need to apply the limits here. So the limits are from A0 to AT, that is the initial concentration, to the final concentration. So I've written here log A from A0 to AT. Similarly, here the K is a constant, it remains as it is minus K. Integral of dt was T from the limit 0 to T. So when we apply the limits, we get it is log AT minus log A0. Okay, log of final value minus the log of the initial value. But log A minus B is nothing but log A upon B. So instead of writing it as log AT minus log A0, I can mention it as log AT upon A0. Okay. Similarly, on the right hand side, T from the limit 0 to T. That means final value minus initial value. So it is simply T minus 0, which gives me T. So I have the expression log AT upon A0 equals minus KT. Now, we can remove this negative sign and write the expression with a positive term. So when I remove the negative sign, then this ratio will get reversed. Because remember, this is log AT minus log A0 equals minus KT. So when I remove the negative sign, it becomes log of A0 minus AT, and log A0 minus AT can be written as log of A0 upon AT. Now taking the t to the left hand side, I have k equals 1 upon t into log of a0 by at. Now this log is natural log. Okay, so this is log 1 by x dx is integral 1 by x dx is log x, but that log is a natural log. So natural log means the base of this logarithm is e. So we need to convert this into log to the base 10. All right, because for numerical purposes, we always consider the logarithmic values to the base 10. So in order to convert this to log to the base 10, I multiply it by a factor of 2.303. So now the expression becomes k is equal to 2.303 upon t into log to the base 10 a0 by at. So make a note, students, that this log, which I've written as ln, is natural log. It's called as natural log because the log is to the base e here. Okay, the exponential term e. So in order to convert it into log to the base 10, we need to multiply the natural log with a factor of 2.303. So now this equation that I've highlighted is one way of writing the integrated rate law for the first order reaction. Okay. Now we can also modify this equation and write it in some other forms. So let us once again consider this form, log AT by A0 equals minus KT. Now, you also know that according to the rules of logarithm, log a to the base x is equal to y. Then I can say x raised to y is equal to a. Similarly, here the base is e. So I get e raised to minus kt will become equal to at upon a0. That is what I have written here. At upon a0 is equal to e raised to minus kt. This is going by the laws of logarithm. Okay. So this, when I rearrange, I can say AT is equal to A0 into e raised to minus KT. So this is the exponential form of writing down the integrated rate law for a first order reaction. Okay, so now we have seen two ways of writing the first order reaction. One is k equals 2.303 by t log to the base 10 A0 upon AT, where k is the rate constant for that reaction, t is the time required. Okay, a0 is the initial concentration and AT is the concentration of the reactant at this time t. Then we saw the second way of writing down the integrated rate law, that is concentration at any time t will be equal to the original concentration of reactant multiplied by e raised to minus kt. Okay, now there is yet another way, a third way of writing down this integrated rate law. For that, let us assume the original concentration of the reactant is denoted by small a. Okay, that is at t equal to 0. That means this is the original concentration. Now what will be the concentration that is consumed by the time t is over? So let us say the amount of a or the reactant consumed in the time t is equal to x. That means my concentration of reactant after the time t will be denoted as a minus x. So we have to substitute these terms in the first form of writing the integrated rate law. So I get k equals 2.303 upon t log, instead of writing this a0, now I'm substituting a0 is a. So I put a here in the numerator, and instead of this at, we are going to put a minus x, where x is the amount consumed in the time interval t. So I get log of a upon a minus x. Okay, so the first and the third formula are things which you can use for your numerical calculations, whereas the second one is just the exponential form of writing the integrated rate law. So you should be aware of all the three ways of writing down the integrated rate law for the first order reaction. And this derivation is very important. So see that you're able to derive these expressions. Okay. Now let us understand this integrated rate law of first order reaction using the graphical representations. So first we will consider the differential rate equation which we had written down. That is minus dA by dt is equal to K into AT. The minus dA by dt is the rate of the reaction by definition of average rate, whereas K into A is the definition of rate of reaction using the rate law. Okay, because it's a first order reaction, we have rate is equal to K into A. So when we equate these two, we get this expression which is called as the differential rate law. So now this differential rate law, I can express it as y is equal to mx. Okay, generally we define a straight line by using the equation y equal to mx plus c. Now in this particular equation, there is no c term or there is no y-intercept because here the c is equal to 0. So we have this equation in the form of y equal to mx. Now this indicates that when we plot a graph of the rate of the reaction, that is dA by dt is the rate of the reaction. In terms of reactance, so the negative sign is there. That means the concentration of reactants are decreasing. But this term on the left hand side indicates the rate of reaction. So when I plot a graph of the rate of reaction on the y-axis with respect to the concentration of the reactant on the x-axis, okay, as I've denoted here, then we get the slope of that particular line will be equal to k, and since there is no y-intercept, this line will pass through the origin. That means the graph of rate versus concentration of reactant has a linear relationship. So as the concentration of reactant goes on increasing, the rate of the reaction also goes on increasing. All right. Now let us see one more graphical representation. Now we have taken the integrated rate law for the first order reaction here. So I can write the integrated rate law as K equal to 2.303 by T log to the base 10 of A0 by AT. Now going back to the equation with a negative sign. So when I put the negative sign here, this value of the fraction will get reversed. So it will become AT upon A0, right? Now this I can rearrange and bring it to the form of y equal to mx plus c. Okay, because they are all having a straight line graph you will obtain. So when I rearrange this, I get minus kt by 2.303 equals log at by a0, and this log at by a0 can be written as log at minus log a0. So when I rearrange this, I get minus kt by 2.303 plus log a0 equals log at, or in other words, log at equals minus k upon 2.303 into t plus log a0. So here, now this is of the form y equal to mx plus c, right? So this tells you that if you plot a graph of log of concentration of reactants with respect to time, then you will have an intercept on the y-axis, which is the value of which is the logarithmic value of the concentration of the original concentration of the reactant. Okay, and this slope here is a negative term. So this negative term indicates that this graph is going to have a decreasing slope. So have a look at the graph here. So here on the y-axis we have log of concentration of reactants to the base 10. On the x-axis we have time. So you can see the y-intercept is log of A0, that is the initial concentration of the reactant. And as the time advances, the concentration of the reactant decreases, and hence the log value also will decrease. So you get a line which is pointing downwards, or the slope of the graph is going to be negative, and the slope will have the value minus k upon 2.303. So you could have number of questions based on these graphical representations. So hope you have understood the way these graphs are represented and how to read this graph and understand it. Okay. Now we also have the exponential term for writing the first order reaction, right? So let us take that one now. K equals 2.303 by T log of A0 by AT. Now this I can also write in the form of y equal to mx. Okay, I keep the A0 by AT as it is without separating it out like we did in the previous case. Then I get log A0 by AT equals K upon 2.303 T. So this is of the form y equal to mx. There is no y-intercept, so I have indicated the c in a different color. Okay. So now again, as this equation suggests, this graph is going to be a linear graph passing through the origin, and there will be a linear relationship between log of A0 by AT and the time. Okay, that means as time advances, the ratio of A0 by AT, that will also increase. Okay, that means the logarithmic value increases, means the ratio of A0 by AT has to increase. So that increases, and initially it is 0. So from 0 it goes on increasing. You can see the slope is a positive term, that is k upon 2.303. So as time increases, the log value of A0 by AT also increases, indicating a linear relationship between them. Okay, so these were the graphical representations for the first order reaction. I hope you've understood the derivation of the integrated rate law as well as the graphical representation. Okay. Now we move on to a very interesting topic, that is the half-life of a first order reaction. Now before we understand what is the half-life for a first order reaction, let us try and understand the meaning of this term half-life. So as the name suggests, it is the time required. Life always is a period, right? So it is a time required for the original concentration of the reactant to reduce to half its value. Okay, so when you consider any reaction, whatever time is needed for the initial concentration of the reactant to become half of its original value, that will be known as its half-life. And we denote this half-life by the symbol T half. So what is the expression for the half-life of a first order reaction? Okay, this is again a very important derivation. So at half-life, that means when the time becomes equal to the half-life of the reaction mixture. So we can say that means T equals T half. Then at that point of time, the concentration of the reactant, okay, will be equal to half the original concentration. That means it becomes A0 upon 2. So we just have to substitute these conditions in our integrated rate law for the first order reaction. So here we have the integrated rate law, that is K equals 2.303 by T log of A0 by AT to the base 10. So if I substitute T as T half and AT as A0 by 2, then I have K equals 2.303 T half, that means at half life, log of A0 upon A0 by 2. So when you simplify this expression, this is A0 divided by A0 by 2. That means it becomes A0 multiplied by 2 upon A0. So your A0 cancels and you have simply log 2. Okay. So we have this log 2. Now what is log 2? We can look up the log tables and we find that the value of log 2 to the base 10 is 0.3010. So now we can multiply 2.303 into 0.3010 upon T half. So when I multiply, I get K equals 0.693693 upon T half, or on rearranging, T half equals 0.693 upon K. So this is the half-life for a first order reaction. So you may be asked to derive this expression, or you have to calculate the value of T half when the rate constant is given to you, or calculate the rate constant if T half is given to you, and so on. Okay, so very important derivation and a very important relationship. Now, why is this relationship so important? That T half equals 0.693 upon K. If you can see here, all the terms in this expression are constants. Okay, K is the rate constant. So that means the half-life of a first order reaction does not depend upon the original concentration of the reactant. So irrespective of whatever amount of reactant you have started with, a first order reaction will always have the same half-life. So let us understand this better with the help of this graphical representation. So as you can see here, this is a plot of the concentration of reactant in molarity, okay, with respect to time in seconds. So here the original concentration of the reactant is 0.20 moles. Okay. So now for it to become half the original value, that means the value of the concentration of reactant should become 0.10. So to come from 0.20 to 0.10, what is the time required? So at 0.20, the time was 0 seconds. That was the initial time. Okay, initial concentration. So before the reaction began, so therefore time is 0 seconds. Now when the concentration has decreased to 0.10, that means half the original concentration, the time required has elapsed from 0 to this dotted line. When you bring it down, okay, it comes to 7 here. That means the time required was 7 seconds. So this red line indicates the half-life of the reaction when the concentration changes from its initial value of 0.20 to 0.10. Now let us assume the initial concentration is 0.10. And from here, how much will be the half-life? if it has to decrease to half its value. So half the value of 0.10 means 0.05. So to come from 0.10 to 0.05, what is the time required? So when the concentration is 0.10 molar, the time required, the time is 7 seconds. And for it to decrease to 0.05, the time required is 14 seconds here. Okay, that means the difference 14 minus 7 is again 7 seconds. So you can see the value of the second half-life is same as that of the first half-life. It is also 7 seconds. Similarly, when you see the third half-life, initial concentration is 0.05. At that time, the time is 14 seconds. Now, when you go from 0.05 to half of its value, that means roughly around over here, that is 0.025. Okay, so at this point of time, you can see the time required comes to 21. That means from 14 seconds, it has gone up to 21 seconds to reduce to half its original concentration. So the third half-life again is 21 minus 14, that is 7 seconds. So as you can see here, irrespective of what the original concentration is, for the first half-life, the original concentration was 0.20 molar. For the second half-life, the original concentration was 0.10 molar. For the third half-life, the original concentration was 0.05 molar. But irrespective of what the original concentration of the reactant is, the half-life remains the same. Okay, each time the half-life is 7 seconds. That means the length of the half-life is constant. And this we can understand from this expression that half-life for a first order reaction is 0.693 upon K. That means it is independent of the original concentration of the reactant. Hope you have enjoyed my session. So that's all for today. Thank you. Keep watching and please do share my videos with your friends and ask them to subscribe too. So see you in my next session with the integrated rate law for the zero order reaction. And yes, we do have a small bit of the first order reaction also to be completed. So until then, keep watching and do subscribe and share it with all your friends. Thank you.